All right, let's get the, here we go. All right, so I'm sharing my lecture notes. Oh, here they are. So we're still working now with functions. Okay, you know, we're still in functions. And we saw last time that you can actually get a function from a graph that's drawn in the Cartesian plane, you know, the XY plane that is. If you can't see the slides or you can't hear me, just say something, okay? But again, we saw last time that we can graph a function. We can get a function from a graph. We have that vertical line test. And we also saw that we can get functions from an equation that's drawn in, from an equation that's in two variables, x and y. We can get a function from that as well. Essentially, you just sketch the graph and you want to see if it passes the vertical line test. And if it does, we have y as a function of x, which is really what we mean by function now. Y is a function of x. You know, you have y equals f of x, where f is the function. All right. Okay, so we also saw what the domain of a function is. Remember, that's the collection of all numbers that can go into the function as input that yield a reasonable output. Okay, so that's what the domain of a function is. I mean, the definition of it at least. It can be tricky to find, not so much if you have a relation. If you have a relation, you just look at the x coordinates. For an equation though, and a graph, it can be kind of tricky to get the domain. So I thought it'd be good to write these as rules. Last time I did have these as rules, but here I'm writing them more like procedures. You know, to get the domain of this, use this. If you have this, do that, that kind of thing. So for instance, let's say we have w over g of x. Let's say you have some function written that way, where w is just something written in terms, some expression written in terms of x. You know, it could be a constant, it could be, you know, x plus 1, whatever. The domain then of this quotient, it's all x such that g of x is not 0. The domain is all x such that g of x is not 0. And basically, how do you find the domain in that case? What you want to do is you determine where the denominator is 0, and you basically say the domain is everything except those numbers. The domain's everything except those numbers. The domain of w, I mean, you do technically have to take into account, we're not going to do that here. That's really more when you're dividing functions. But again, for now, the domain, it's all x such that the denominator is not 0. And again, you basically determine where the denominator is 0, and the domain is just everything else. For the square root of g of x, again, g of x is a function. The domain here is all x such that g of x is non-negative. The radicand is greater than or equal to 0. That's what's happening here. And now number 3 in a sense combines 1 and 2. Here you have w over the square root of g of x. For this, the domain would be all x such that g of x is strictly greater than 0. So if you have the square root of something in the denominator, you want to know when that denominator, the radicand that is strictly greater than 0. And again, the domain of w, we're not going to worry about that for now. I mean, I don't think we'll get to that though, but that's okay. But again, this is just basically how you can find domain of a function from an equation. Yeah. Good. So for instance, I think we saw this last time, y equals 1 over x. The only time the denominator is 0 is when x is 0. So the domain would be everything else, all non-zero numbers. For the square root of x here, right, the radicand is just x, so the domain is all x, such that x is non-negative. As an interval, you can write this. And also, when you have 1 over the square root of x, again, you want to know when the radicand here is strictly greater than 0. I'm basically using this, where w is 1, g of x here is just x. So you want to know when x alone is just greater than 0. Well, so the domain would be all x, such that x alone is greater than 0. As an interval, you have this. You're just basically taking the previous and removing 0. So that's what it boils down to. All right, so let's do some examples of this. For instance, we have 1 over 4x minus 8. So we want to know when what the domain of this is. Well, again, it's where the denominator is not 0. It's where the denominator is not 0. So for 4x minus 8, we want to know when is that equal to 0? Well, we solve. We have an equation, right? So we add 8 to both sides. And we get 4x equals 8. Then we divide both sides by 4, right? Because again, for solving this equation, we want to know what x is. So we're getting x all alone. Divide by 4, we get x equals 2. Let me go through it again because I think I went kind of quick. Add 8 to both sides. We have 4x equals 8. 4x over 4 equals 8 over 4. Divide both sides by 4, we get x equals 2. So the domain then, right? So this is 0. The denominator is 0 only when x is 2. So the domain is all x such that x is not 2. So everything else is in the domain. And to really show this, I sketched the graph. I sketched it in Desmos. This is what the graph's going to look like. Actually, you know what? I got a better idea. I mean, this is good, but let me also sketch it let me also show you in Desmos how I got the graph. I think that would be smart. If you have a graphing calculator, that's fine, but if you don't have one, that's okay also. You don't need one for this class because of Desmos. All right, so let me just stop sharing this for a second. And we have, this. All right, so hopefully they can see it. Good. So again, if you click on Math Tools, Graphing Calculator, here it is. And you could type y equals 1 divided by 4x minus 8. And you can see we get the graph. There's also a keyboard here. It says show keyboard. You could type it in this way as well. On the slide, I also drew x equals 2, as you can see. And again, the graph gets closer and closer to x equals 2, that vertical line. Excuse me, but it never actually reaches it. No part of the graph is above or below 2. Which basically means the graph is not defined the function is not defined at 2. Okay. I mean, you don't really have to use Desmos if you don't want to. I just thought it was really nice because it's free. So I thought that'd be a good idea. But I did graph it. If you ever need help using it, don't be afraid to ask me. I'll be more than happy to help you. All right. I want to get back to the lecture notes now. Okay, I'm going to stop sharing this. Booyah. Booyah. There we go. All right, awesome. So here's our next example, right? What we want to do now is get the domain of this thing. We have a square root, right? So here we want to know when the radicand, the 2x plus 7, right? The radicand is what's under the square root, when that is non-negative. Okay, so what do? We have an inequality to solve, right? Again, inequalities are similar to equations. The steps are similar. You want to isolate x. So we're going to subtract 7 from each side, right? Subtract it from each side. Then we're going to have 2x on the left, greater than or equal to negative 7. We're dividing now by 2 because you want to get x all alone. So we get x is greater than or equal to negative 7 over 2, which is negative 3.5. Notice I did not turn the inequality around. You only do that when you're multiplying or dividing by a negative, but 2 is positive. So we have this thing here. The domain then is all x, such that x is bigger than or equal to negative 3.5. So it's all x such that x is greater than or equal to negative 3.5. So in other words, we get this interval. And did I graph this? Absolutely. Remember, I did email everyone the notes, so you should have these slides in front of you. But this is what the graph of it looks like. Again, I drew this using Desmos. So it's defined over negative 3.5, and it's defined to the right of it, right? You know, if you're anywhere to the right, you go up, you get to the graph. So that number will be in the domain. Everything to the left of negative 3.5, well, that's not defined. Okay? That's not in the domain, I mean. Yeah? Question?
So so x cannot equal negative 3.5, and x is greater than or equal to 0?
No, we want 2x plus 7 greater than or equal to 0. And we solve the inequality to determine when that happens. And that happens exactly when x is greater than or equal to negative 3.5.
Oh, so this one isn't when x like doesn't equal 0 in this one?
No, not this one, no, because you have a square root here. When you have
okay.
when you have the square root in the denominator, like in the next example, that's when you can't have 0. You'll see what I
So
mean.
only when it's in the denominator.
Exactly, because you can't divide by 0. That's a no-no.
Right. Okay. Thank you.
You're welcome. Very good question. But here, well, oh, sorry, wrong way. Here, you can have the function equal to 0. That happens when x is negative 3.5. That's okay, because there's no denominator here. Awesome question.